Right. So one of the biggest things in statistics that we want to be able to do is to estimate a parameter. Remember, a parameter is a number that's associated to the population. So for example, a number that's associated to the population could be the mean. So what is the average height of people, or what is the average weight, or what is the average blood pressure, or something like that. It's an average amongst the population. Another parameter that we could try to estimate would be the proportion. So for instance, what percentage of people have brown hair, or what percentage of people write with their right hand, or what percentage of people are going to vote for Donald Trump, or what percentage of anything, this proportion. And so ultimately what we want to do for a population is we want to estimate that parameter. Now, the best way to get the parameter is to actually take a census. If we could get a census and ask every single person in a non-biased way, then the numbers that we get, we could actually use to form our parameter. But a census is not feasible, and oftentimes it's too expensive, so there are other ways to get around that. And so what we do is we take samples. Now, using the central limit theorem, we know that samples in general tend to stay near the parameter. So if we know that samples tend to stay near the parameter, we can use a sample and the fact that it must be near the parameter to estimate that parameter. So if I know that 95% of all samples are within 5 from the sample mean, so that if 95% of all sample means are within 5 from the sample mean, then I know that the parameter, the population mean, must be within 5 of, has a 95% chance of being within 5 from the sample mean that I end up getting. And so that's what we're going to be doing today. So the first way to estimate a population parameter is by using a point estimate. A point estimate is a single number estimate for the parameter. The most obvious point estimates are those that we can take from our samples. So if you have a population mean, mu, you can use a sample mean. So if I wanted to figure out the sample, if I want to know the population average height, then I can take a sample of 100 people and find their height, and then take that average, and that's what I would use as an estimate, a single number estimate for the population's average height. For a proportion, p, I can use p hat. Now, p hat is just a sample proportion. So if I want to estimate the percentage of people that write with their right hand, I can do that by taking a sample of 100 people and figuring out how many of those write with their right hand, and use that as an estimate for the population's percentage. And lastly, if I want to look at the difference between means, so if I want to know how much taller men are than women, I could try to estimate that by saying, okay, the population mean of men is mu1, and the population mean of women is mu2. And if I want to figure out, if I want to make a guess at that, I can use the sample average, so take a sample of men and take their average, take a sample of women and take their average, subtract those two numbers, and that will give me a good estimate for the difference for the actual population means. So the very first thing we should do is estimate, and we use a single estimate, point estimate, and that's good enough for a point estimate as to what we're trying to do. We're trying to estimate those parameters. A point estimate's not perfect though, because what ends up happening is, although that number is probably pretty close to the population parameter, we don't know how close it is. And so what we'd like to do is give an interval estimate. So we'd like to say, we believe the population mean, the average height of people, is in between this number and this number. And when we do that, that allows us, that interval estimate allows us to kind of pinpoint a bigger range of where the population parameter must be. With any interval, we'd like to say how confident we are. Do we really think that that's where the population parameter is, or do we think that it's probably kind of in that area? And that level of confidence is the probability that the parameter actually falls inside that interval. So I would like to say something like, we believe that the average height of cats is between 10 inches and 12 inches, and we are 95% confident that that is true. It's a pretty high level of confidence. It is very, very likely that that's actually true. The way that we get that level of confidence is based on the central limit theorem, because we know that samples have statistics that are close to the parameter, we can say how probable it is based on the sample size that we're actually landing in a certain region. So that level of confidence is going to be built based on the central limit theorem. A confidence interval is an interval estimate along with a set level of confidence. So if I say that I'm 95% sure that a number falls between 10 and 12, the 10 and 12 is the interval, the 95% is the level of confidence. The confidence interval then is those two things together, how confident I am that that's true, and then what the actual interval is. And the margin of error is the largest possible distance from the point estimate that a confidence interval will cover. So what ends up happening is, when we talk about these types of things, we basically say that the margin of error, which I'm going to put as E for error, if I take the sample mean that I get and add or subtract that error, this whole thing is going to give me an interval. So for instance, say that I get a sample mean of 11 inches and I get a margin of error, so I try to figure out how confident I am. I want to be 95% confident. And if from that tells me that I could be off by 1 inch, then if I take 1 from 11, I get 10 inches. And if I take 1 and add it to 11, I get 12 inches. So that interval that I get is 10 to 12 inches. The margin of error is basically, I take my point estimate, how far off could I be based on the level of confidence that I'm using, and that gives me my confidence interval. So the confidence interval and the margin of error, these kind of go hand in hand. They tell you how to describe where the population's parameter is. The way that the margin of error is going to work is it's going to work on two pieces. The first piece is the z value. So the z value really corresponds to the distribution that we have and the fact that we know that the population parameter lands in the middle of that distribution using the central limit theorem. So the confidence level is telling us the z-scores, how far we need to go out so that we can get that 80% or 85% or 90% or so on and so forth. So if we want to be 80% confident, that corresponds to going out 1.28 standard scores or standard deviations away from the mean. 1.28 on either direction. And that area there will give me 80%. So if I know how confident I want to be, I'm going to use that z-score to kind of make the prediction, and we'll see how that works in just a minute. But the first thing we'll do is we'll talk about the critical z-score table, which associates to each confidence level a z-value or a z-score that I'm going to use to build my margin of error. So this is, when I talk about the critical z-value table, I'm talking about looking up my confidence level on here, finding the associated z-value. Once I have that z-value, that z alpha over 2, that is that critical z-value. If you want to know where the alpha over 2 is coming from, alpha over 2 comes from the idea that in a normal distribution, we can kind of split that area in 2. So over 2, we're kind of splitting that alpha over 2, and the alpha is corresponding to the confidence, level of confidence. So if we're talking about sample means and using a sample mean to make a prediction on the population mean, the parameter, then the margin of error for that is going to be to take z alpha over 2, the critical value off from the z-score table, and then we're going to take that and multiply it by the standard deviation of the distribution. The standard deviation of the distribution, as a reminder, is equal to the standard deviation of the population divided by the square root number of n, and so that's where we're using our central limit theorem in order to make a prediction on the population parameter. So the way that this is going to go is we're going to make a point estimate by taking a sample. So we take a sample, say of 100 people. We get our point estimate because we can actually take the average from that sample. Once we get the average from that sample, we'd like to say with confidence, some confidence interval of where we think the actual population average is, or the population mean is. So we take once we know our confidence, we're going to take that level of confidence, find the z over 2 on the table. If we know the standard deviation of the population, we'll divide by the square root number of n because we know how big our sample was. That gives us the standard deviation. Once we have the standard deviation, We can multiply it by the z alpha over 2 that we got from the table. That gives us our margin of error. And then we can take our point estimate. And if we have our point estimate, we can add or subtract the margin of error. That gives us a confidence interval with the associated confidence that we want. So here I want to do an example. So suppose that we know the standard deviation. So suppose that we're trying to measure some animal and see how tall it is. You could pick whatever animal you want. So I'm just going to leave that open-ended. But suppose that we know that the standard deviation of that animal for its height is 2 inches. So then what we're going to do is we're going to take a sample of some size. Let's take a sample of 100. So we're going to try to predict 100 of whatever the animal is. And we get a sample mean of, let's say, we get a sample mean of 9 inches. So we got a sample mean of 9 inches. And we want to, let's say we want to predict the actual population mean with 95% confidence. So with 95% confidence, let's estimate the population mean. So the idea here is that there's a population of all of these animals out there, and we'd like to know what the average height is of all of these animals. We took a sample of 100 of them, a simple random sample, and we got an average of 9 inches. So we want to, with 95% confidence, estimate that mu. So there's a couple of things we need to know. We need to know the z alpha over 2. For 95% confidence, the table tells me that I get 1.96. So for z alpha over 2, 1.96. So I need to be 1.96 standard deviations away from the mean. It's pretty close to 2, and that's because 95% confidence kind of corresponds to 2 with the empirical rule. So this is all related. The next thing is the margin. So to get the margin of error, the next thing we need to know is we need to know the sigma x bar, and that is equal to sigma 2 divided by the square root of the sample size, divided by the square root of 100, which is equal to 2 over 10, which is equal to 0.2. So now we can use that formula from the previous slide for the margin of error, and the margin of error is going to be 1.96 multiplied by 0.2. And so let me do that calculation really quickly. So 1.96 times 0.2 gives me 0.392. And what we're going to do then is our confidence interval is going to be the point estimate, 9, plus or minus the margin of error, how far we could be off, 0.392. And if I take 9 minus 0.392, I get 8.608. And if I take 9 plus 0.392, I get 9.392. And this is my confidence interval. So now, here's the statement that I can make based on this. I am 95% confident that the average height of this animal is in between 8.608 inches and 9.392 inches. So again, you're going to take your level of confidence, find your z alpha over 2, your z-score, your critical z-score, and then multiply that by the standard deviation for the distribution. That gives you your margin of error. So then you can add or subtract that to your point estimate, which is your sample average. And then that tells you how far off you could be. And so you add or subtract that, and it gives you an interval, and that interval corresponds to the confidence that you start out with, which is 95% confident. That game gets played for every single possible distribution of sample mean, sample proportion, sample differences. So the margin of error for a sample proportion looks remarkably familiar because the central limit theorem tells us that the standard deviation is, well, it's p times 1 minus p over n. Now here we use p hat because the idea is that we're going to get a population proportion by using the estimate from our sample proportion. So we're going to take a sample, we're going to get a proportion. With that proportion, we're going to use that to actually plug this in for the standard deviation of the distribution, which would be this part. We're going to multiply by the z alpha over 2 based on our level of confidence, which comes from the same critical z-score table. Once we do that, that gives us our margin of error, and we do the same exact game that we did the sample means. And then for the margin of error for the difference of means, again, I'm going to do a point estimate. That point estimate is going to be based on the mean that I get from each sample. And then I'm going to need to know my margin of error. The sigma 1 squared, that is the standard deviation of the first population. So this is standard deviation of the first population. So if you're doing like a male versus female type of thing, this would be the standard deviation of the males. This would be the second one would be the standard deviation of the females. So this is the standard deviation of the second population. The number N1, which would be the number of people in the first sample. Number in sample 1. You usually try to get this probably to be the same, but what if you have someone drop out or not answer, right? And so your samples would be different. Number in sample 2. Z alpha over 2 again is going to come from that critical z-score table. And so then you'll get your margin of error. Your point estimate would be x1 bar minus x2 bar. This is your point estimate, and then you're plus or minus the margin of error, which comes from that formula up there. So let's do some examples. So suppose that you want to estimate the percentage of people that write with their left hand. So what you'll do is you'll take a sample of some size. So let's say that you want to be with 80% confidence. You want to know the percent that write with their left hand. Okay, so from this, you need to take a sample and find that percentage. So suppose that you sample, let's say you sample 20, well, let's say you sample 36 people. You sample 36 people. And let's say that 18 write with their left hand. These are made up numbers, by the way. So then you can compute your p hat. So p hat would be equal to 18 over 36, which is equal to 0.5. From this, you can try to get your margin of error. Your margin of error would be equal to z alpha over 2. So you take that 80% and you get your z alpha over 2 from the table, which is 1.28. So the margin of error is 1.28 multiplied by the square root of p hat, 0.5, times 1 minus 0.5, this is from that formula, over number of people you asked, which is 36. And so what you end up getting is you get 0.5 times 0.5, which is 0.25 or 1/4, over 36. You're going to take the square root of that, so we just have to multiply by the 1.28, which is equal to 1.28 multiplied by the square root of 1 over 144, which is equal to 1.28 multiplied by 1/12. If you take the square root of 1 over 144, you get 1/12. So if I do that on the calculator, I get 0.106666 repeating. So 1.1067. I'm going to round it to that. Now, your sample proportion was 0.5. So for your confidence interval, you're going to take 0.5, add or subtract it to the margin of error, which is 0.1067. And this is going to give you, so if I take 0.5 minus 0.1067, I get 0.3933. 2, and then I get, if I add that, 0.6067. So it's 39.33% to 60.67% would be my confidence interval. So I can say that I'm 80% confident, if this is the sample that I got, I'm 80% confident that between 39.33% and 60.67% of people write with their left hand. I'm not that confident, and I'm not landing exactly where I want to land. Why? Now, if I go back and look, the sample of 36 people is a small sample. And because it's such a small sample, I'm getting a really big variety between my lowest number to my highest number. If I want to be more precise, I need to get that margin of error to get smaller. One way to get the margin of error to get smaller is to get that number 36 to get bigger. If it gets larger, then the standard deviation of my distribution gets smaller, which makes my margin of error get smaller, which makes it so that I can pinpoint more closely what the actual population parameter is. The last one, which I'm going to skip the example for right now and leave that for office hours, is an example on the difference of means, but it works out the exact same way. So I'm just going to kind of summarize what you would do. If you want to find the difference of means parameter, then you're going to take a sample mean from your first sample and a sample mean from your second sample. Your point estimate is to subtract those. So if you get 5 and 7, subtract. 5 minus 7 is -2. How off could that -2 be? That -2 could be off by the margin of error. So you can take your level of confidence, look up your critical z-score, multiply it by your margin of error from the formula from the previous slide, and that gives you the margin of error. So you can take -2 plus or minus that number. And the point is this, that -2 corresponds to the difference of the population means, which means that if I was trying to figure out if, say, males are taller than females, and I got the male average minus the female average is -2, that would actually mean that the height that men are taller than women is -2. That would actually mean that men would be shorter than women. And how far off could I be? I would add or subtract my margin of error to get my confidence interval. And so that negative or positive number is telling you how big or small in comparison that first sample is to the second sample. And that's it for the chapter 8 and the start of chapter 9 stuff. So I'm going to stop here, give you some time to think and try to practice this out, and then we'll talk next time.